Hi, and welcome to 2.5 Graphing Motion Acceleration. In this lesson, students will be able to analyze a v versus t graph to find the acceleration and the displacement. So now you'll be able to do d versus t and v versus t. Just as a review, in a d versus t graph, what does the slope represent? Pause the video, think about it. The slope represents the velocity. Why? Because here's the slope formula. The y values is the displacement and the x values is the time. And our reference table tells us that the physical quantity that's equal to the change in displacement divided by time is velocity. The equation looks like this: v is equal to d over t, which is what we have here. So therefore, the slope is equal to the velocity in a displacement versus time graph. For a velocity versus time graph, what does the slope represent? And then we could actually determine another physical quantity from velocity versus time graphs by looking at the area under the curve. So first of all, the slope looks like this. And your y values now are the velocity and your x values are still time. And our reference table tells us that the physical quantity that's equivalent to delta v over t is, what do you think? Acceleration. We learned that a is equal to delta v over t in the last video. But what about this weird term area under the curve? First of all, I don't see a curve here. I see a straight line. Well, in math, they call the function the curve. So even if it's a straight line, that you could still call it the curve. And the area under the curve, let's say you want to know after 3 seconds, what is the area under the curve? Isn't that just a rectangle? And what is the equation for a rectangle, for the area of a rectangle? It's the length times the width. And now the length is velocity and the width is the time, the y and the x values of that graph. So length times width becomes velocity times time. So which physical quantity is equivalent to velocity times time? It actually goes back to this first equation. If you cross multiply, you get d is equal to v times t. And there's our v times t thing that we're looking for. So that's equivalent to the displacement. So the slope represents the acceleration, and the area under the curve represents the displacement in a velocity time graph. Critical thinking: are these graphs representing the same motion? What do you think? Well, let's look at the displacement time graph here, okay? In the displacement time graph, the slope is the velocity, and I see the slope is not changing. So that means the velocity is not changing. So we have a constant velocity. This thing is moving, but it's not accelerating. It's just moving at a constant velocity. Tell me about velocity versus time graph down here. How would you describe that motion? Well, I don't see the slope is equal to 0. So that's one way we could think about it. And if the slope is equal to 0, the acceleration is 0. And if you're not accelerating, that's right, you have a constant velocity. What's a different way? You might have looked at the y-axis first and been like, Mr. Nangle, it's always staying at the same y value. So that means it's always staying at the same velocity. So that means, again, a constant velocity. So to answer the critical thinking question, are these graphs representing the same motion? Yes, even though they look different. This one looks like it's pointing upwards. This one is horizontal. They look like different graphs, but they're representing the same motion. Okay, what are some more examples of these different graphs that represent the same motion? Let's take a look. For stationary, what would you predict the displacement versus time graph to look like if it wasn't moving, if it was stationary? Maybe it's 5. If you said this, that's totally fine. That means it's at the origin. That's what I was going to predict, but I did it like this on purpose. I forgot. So it's staying like, let's say this is 5 meters away from you, and it's constantly 5 meters away from you. That means it's not moving at all. What would you think the velocity time graph looks like for a stationary object? That's where it's definitely at the origin because we want the velocity to be 0 because it's stationary. How about something moving with a constant velocity? Do you remember the graphs from the previous slide? What did that d versus t graph look like? Remember, the slope is the velocity. So we want a constant slope, a slope that's not changing. Now, what does the velocity versus time graph look like? For constant velocity, it's not 0 anymore. Technically, you could say, oh, this is a constant velocity of 0. That's totally fine. But we have a constant velocity where we're moving, and it looks something like that. The next one is increasing velocity. So you're accelerating. Your velocity is changing. So if your velocity is changing, that means your slope must be changing. And if it's an increasing velocity, we want an increasing slope. What do you think that looks like? Looks something like that. Something like that. And what do you think that? How would we represent that motion on a velocity time graph? Remember, we want a increasing velocity. So we can make it look like this, where there's a constant acceleration. You're constantly changing your velocity at the same rate. Now you could have a increasing acceleration. So we have an increasing velocity here. The next one is an increasing acceleration, which is called a jerk. But Mr. Nangle's enough of a jerk, so we don't need to get into that in this class. Plenty of jerks in this class. Example 1. So let's do some calculations. We were just kind of doing an overview before. It says the graph represents the relationship between speed and time for an object moving along a straight line. What is the total distance traveled in the first 4 seconds? So the first thing I do when I'm faced with a graph question, now that we know d versus t and v versus t graphs, I need to identify what's on the y-axis. So this is speed versus time, and we could use velocity versus time graph, things that we know that we've been talking about. It's interchangeable, okay, for these purposes. So we're looking at a velocity time, speed versus time graph. What do we know about those two graphs? We know that the slope is the acceleration, and the area under the curve is equal to the displacement. So once I identify what's on my y-axis, and I remind myself, okay, now that I know what type of graph I'm looking at, this is the rules for that type of graph, then I could look at the question and it says, what is the total distance traveled in the first 4 seconds? And if they're looking for distance or displacement, I better find the area in the first 4 seconds. So something like this. Okay, so the area under this curve between this curve and the x-axis. So what shape did I just draw? A triangle. And we have to find the area of this triangle. So the area of a triangle formula looks like this. And I believe that's on page 5 of your reference table in the geometry section, just in case you forget what the area of a triangle is, 1/2 base times height. So we just couldn't write, I'll write it underneath, the area is equal to 1/2. The base is 4 seconds. And I'm going to write the units so I don't get points off for units. And the height, what's the height of this triangle? Is it 1, 2, 3, 4? No, no, no. You have to look at the y-axis. The height of this triangle is 20, and what are the units? Meters per second. And then here's something that I didn't explain this way. If we have a second times a meters per second, what unit are we going to be left over with? I'm doing a kind of a tangent here, but just so you know, a second times a meter per second, what unit will that give us? Well, the seconds cancel out, leaving you with just a meter, which is the units for displacement. So that's another way to verify that, yes, I'm doing the right thing. I'm looking for the right value. So what's 4 times 20? You could do it in your head. What's 4 times 20? What's 4 times 2? 8. So 80. What's half of 80? 40. And what are our units? What did we just solve for? The area, which represents the displacement, and the units are meters. So for number A, it's 40 meters. For letter B, it says, what is the acceleration? Well, I know that I'm looking at a velocity time or speed versus time graph, and I know that the slope is equal to the acceleration. So if they're asking for the acceleration, I better find the slope of this line. And to find slope, you need to do y2 minus y1 over x2 minus x1. So pick any 2 points. I'll pick this one, and I'm going to pick the origin just to make my life a little easier. Y2 is up here, 25, minus y1 is 0, and x2 is 5, so over 5 minus 0, x1. So you get 25 divided by 5, which is 5. I'll write it down here so we could have room for our units. Oh no, I forgot to write the units. I got to make sure I do that. Listen, if that happens to you, you could just do this. Meters per second, squeeze it in. I'll accept it. Okay, and then this is seconds down here. Totally fine. Everything is fine. And then the slope of the line becomes 5. And what are the units that we're going to put for the slope of this line? Remember, the slope is the acceleration, and the units for acceleration, meters per second squared. Don't forget the 2. That's a big point right there that you'll get off if you forget the 2. Or these. I know I keep on saying it, but I don't want to have to take off points for that this year. We'll see. Maybe this will be the year where I never take off points for units. Next question. Oh, this one looks weird. Example 2. What is the instantaneous velocity at 5 minutes, the acceleration at 5 minutes, acceleration at 30 minutes, distance traveled after 30 minutes, total displacement? Try this one on your own. Pause the video, see if you could do it, and then I'll do it right now. I'll wait. Pause the video. Okay, now that you paused the video and did the work, let's do this. Instantaneous velocity at 5 minutes. So 5 minutes is here. So we want to know the slope. Oh no, see, I forgot the first step already. The first step, what's your y-axis represent? So now we're looking at a velocity time graph. I said slope because I thought I was looking at a distance versus time graph. Okay, so since it's a velocity time graph, all you have to do is extrapolate the data. At 5 minutes, your velocity is on the y-axis. Looks like 30 meters per minute. What a weird unit. 30 meters per minute. Okay, and we got that just by looking at the y value at this point, okay, in between 20 and 40. So it says, what is the acceleration at 5 minutes? So now that we know we're looking at a velocity time graph, why don't we remind ourselves that the slope is the acceleration and the area under the curve will be our displacement. So the acceleration at 5 minutes is here, and this is where we want to know the slope of this line. So we could pick actually any 2 points on this line and we would get the slope, we would get the acceleration. So I'm going to pick those 2 points. It goes through the origin, so that's sweet. And then we have 60, well really 10, 60 is y, x2, y2. So you get 60 meters per minute minus 0 meters per minute over 10 meters per minute minus 10 minutes minus 0 minutes, and you get 6. Units are going to be meters per minute squared, just like that. Okay, the next one says, what's the acceleration at 30 minutes? So at 30 minutes, we're right here. The velocity is 0, but what's the acceleration? We have to find the slope of this line from here to here, any 2 points along these. Okay, I'll use those 2 points that I just circled. So those 2 points are 15, 60 and 40, negative 40. So this one goes below the x-axis and you have to keep the negative 40 in there. So I'll plug in my numbers there. So this is the second point and this is the first point. So y2 is actually negative 40 and y1 is 60 and x2 is 40 and x1 is 15. So you get negative 40 plus negative 60 is negative 100 divided by 40 minus 13, 40 minus 15, and you get -4 meters per minute squared. So we got a negative number. Does that make sense? Look at your slope. Isn't that a negative slope? And isn't acceleration a vector quantity? And positive means to the right, and negative just means to the left. So it's okay if you get a negative value. -4 meters per minute squared. All right, the next one's a little different. It says, what is the distance traveled after 30 minutes? And we know that a velocity time graph, the area is equal to the distance or the displacement. Oh no, now we have to look. There is a difference between distance and displacement. See, the area here is on the positive side of things. So you're going in the positive direction. But then you go in a negative direction. So you get a negative displacement here. You're moving to the left. So you could have a total distance and then a displacement from here to here. I know my little vectors are a little confusing. Makes sense to me. Hopefully it makes sense to you. Let me know if there's a question about that particular piece, but let's go over the distance traveled after 30 minutes. It's just this positive value here. So we could find this area, but it's a trapezoid. There's a formula for that. I like to break it up into a couple triangles and a rectangle. So you could just drop a line down here, and all of a sudden you have one triangle. Then you could drop another line here. You have another triangle here, and then you have a rectangle right there. So you could do like 1, 2, 3, and then for your area, I'll use those subscripts. The area of the first segment, 1/2 base times height. The area of the second one is length times width because it's the rectangle, and the area of the third one is equal to, again, 1/2 base times height because you're looking at a triangle. So the base of the first one is 10 minutes. And the height of all of these is 60 meters per minute. All right, the base of the second part, what's the second part? Is it 15? No, because each grid line represents 5. So this is 5 long. A2 is equal to 5 minutes times the height again of the rectangle is 60 meters per minute. And then I'll move this over. The third area is 1/2 base times height. So what's your base here? From here to here, we have 5, 10, 15 minutes. And the height is again 60 meters per minute. Got to write those units. So your first area is equal to 300. And what are the units for the area? Well, it's displacement. So we're going to use meters. Again, because the minutes cancel out, leaving you with just meters. The area of the second piece is 5 times 60, which is again 300 meters. And the area of the third piece is 1/2 15 times 60, which is 450 meters. So your total distance traveled after 30 minutes is 300 plus 300 plus 450, or 1,050 meters. Now it's asking for your total displacement. And like I said before, from 0 to 30, your velocity is positive. So you're going in the positive direction. What's happening is you're speeding up, then you're traveling at a constant velocity of 60 meters per minute. And now what's happening? You're actually slowing down because your velocity is positive, but what is your acceleration? Negative. And we said if you had a positive velocity and a negative acceleration, you'd be slowing down. slowing down to what speed? At 30 minutes, you're traveling at 0 meters per minute. And then what happens? Your velocity becomes negative. So you stop for a very split second and then you turn around and go in the opposite negative direction. Okay? And you're speeding up in the negative direction because now your velocity is negative and your acceleration, the slope, is still negative 4 meters per minute. So you're actually speeding up in the negative direction. And then your velocity is negative. Still, this whole leg, your velocity is negative, but what is your acceleration? Is this slope positive or negative? The slope is positive. So now your slope is pointing to the right, and at this point, you're slowing down. So that's kind of the big picture with what's going on here. And here we have 1,050 meters, and we're traveling in the positive direction. But now we're going to travel in the negative direction. What is the area here? So we could again break this into two triangles, and I'll call this triangle 4 and 5 for continuity. Get rid of all this stuff on the bottom. And now we're ready to find the area of those two triangles. So for the 4 triangle, we have 5, 10. The base is 10 minutes long. So area of 4 is equal to 1/2. The base is 10 minutes. And the height, now watch the height. The height of this triangle is -40. And here's where we're going to get our negative numbers. Meters per minute. Okay, so we could do the area of number 4 is equal to -200. And remember, what are the units for area under a curve, a velocity time curve? Minutes cancel out and you're left with meters. So that's a negative displacement. We're moving to the left now. And our area for the 5th triangle is kind of similar, but the base is now 5, 10, 15 minutes long. 1/2, 15 minutes times the height, which is again the same height, -40 meters per minute. And when you do the multiplication, you get -300 meters. So the area under the curve from 30 to 55 minutes is -500 meters. So your total displacement is going to be 1,050 meters plus -500 meters, which is equal to 550 meters. So you go to the right 1,050 from t equals 0 to t equals 30, and then you turn around and you go to the left 500 meters, and your total displacement is measured from start to finish, which is 550 meters. That's your total displacement. What is your total distance that you traveled? Well, here we don't care about the direction, right? So it would just be 1,050 plus 500. Your total distance traveled is 1,550 meters. They didn't ask that, but just in case you wanted to know. All right. A quick critical thinking question. This video is super long, but can you be moving with a constant speed, but still be accelerating? So you're moving with a constant speed, but how can you be accelerating? Is that possible? What do you think? Pause the video, think about it. Is it possible? Yes. Because the definition says the rate at which velocity changes, the acceleration definition, the rate at which velocity changes over time. An object accelerates if its speed, direction, or both changes. So if the direction of the velocity changes, that velocity vector is changing. And any change in velocity gives you an acceleration. So what might that look like? Well, if you're changing your velocity vector's direction, maybe you're moving in a circle or even just around a bend, making a turn. So I want you to think about what direction is the velocity vector pointing on that little car. How would you visualize what the velocity vector might look like? And visualize, this is even tougher, what direction is the acceleration vector pointing? We're going to go over those two answers in Unit 7. We have to do like forces and all this other crazy stuff first, and then we come to circular motion. So there's plenty to unpack with just acceleration and changing the speed before we get into acceleration where you change your direction. But we'll get there in Unit 7. Anyway, that's about it. Seriously, thank you for watching, over 25 minutes long, and have a great day.